Welcome back, everybody. Today we're looking into something that's, well, let's be honest, it's everywhere.
Yeah.
But, it's not something most people spend their days thinking about.
You mean like what makes the universe tick?
Yeah, exactly. Thermodynamics, the study of heat work and temperature. And I guess more generally, how energy interacts with matter.
Mm-hmm.
I mean, think about like how a car engine, how does it turn gas into motion?
Right.
And why can't you just like unscramble an egg?
Yeah.
It's all because of thermodynamics.
Absolutely. It's really quite fascinating.
It is. And it's, the funny thing is, it all started from a really practical problem.
Yeah.
Trying to improve the efficiency of steam engines.
Back during the Napoleonic Wars.
Right. Who knew that like military ambitions would lead to, these really huge fundamental discoveries about the universe?
Pretty incredible, isn't it?
Yeah. Talk about unintended consequences, right? But okay, so before we get to engines and things like that, we gotta lay down the ground rules, the rules of the game, so to speak. And in thermodynamics, those rules are the 4 laws.
Exactly. The 4 laws of thermodynamics, I mean, they're like the fundamental commandments of energy.
Okay.
And the 0th law, I know it sounds a bit out of place, but it's really the foundation. It defines what thermal equilibrium is.
Okay.
So it's the idea that if 2 systems are each in equilibrium with a third, then they're also in equilibrium with each other.
So like if my coffee cup is the same temperature as the table it's sitting on,
Yeah.
and the table's the same temperature as the air in the room, then my coffee is also in equilibrium with the air.
Precisely. They've all reached a thermal truce. Now, the 1st law,
Yeah.
this is the one most people have heard of. They just don't know it's called the 1st law. It's all about energy conservation. Energy cannot be created or destroyed, only transformed from one form to another.
Okay, so like no perpetual motion machines then.
Exactly.
Yeah.
No free lunch.
Right.
Take a closed system, like, say, a sealed container of gas.
Okay.
You can change its internal energy by adding heat or by doing work on it. But the total amount of energy, it always stays the same. It just changes form.
So if I compress that gas, I'm doing work on it, and then its temperature is going to go up.
You got it. Perfect example of the 1st law in action. Now, things get a little more interesting with the 2nd law.
Okay.
This one introduces this concept of entropy, and it's often described as a measure of disorder or randomness.
Oh, entropy. I've heard of entropy, but I'll be honest, it's always been kind of a fuzzy concept for me.
Well, think of it this way. You've got a perfectly ordered deck of cards, all arranged by suit and number.
Okay.
Okay? Now, if you shuffle that deck, you're increasing its entropy.
Okay.
The cards become more randomly arranged.
Right.
And it's far more likely that the deck will end up disordered than that it'll magically shuffle back into perfect order.
So it's like my desk, like left to its own devices, it always gets messier, never cleaner.
Exactly. The 2nd law basically tells us that the entropy of an isolated system, like say the universe, always increases over time. It's why heat flows from hot objects to cold ones, why ice melts in a warm room, and yes, why your desk seems to have that natural tendency toward chaos.
Interesting. Okay, so, but does that mean that eventually everything's just going to end up in a state of like maximum disorder?
Right.
Like some kind of cosmic heat death or something?
That's a question that's puzzled physicists for a very long time.
Yeah.
And it leads us to the 3rd law, which gets into some really mind-bending territory.
Okay.
So, as a system approaches absolute zero, the lowest possible temperature, its entropy, it approaches a minimum value.
So at absolute zero, everything would be perfectly still and ordered. I mean, is that even possible?
When that's the thing, absolute zero, it's a theoretical limit that we can never actually reach. It's like a horizon that we can approach but never actually cross.
Okay.
But the 3rd law, it helps us understand the relationship between temperature and entropy in a very fundamental way.
Yeah.
Even Einstein, he found this concept challenging.
Wow.
So.
Okay, so my head is officially spinning.
Yeah.
Okay, so we've got these 4 laws that govern how energy behaves. But how do scientists, how do they actually study thermodynamics in practice? Is it all just like equations and abstract concepts?
Well, there are different branches of thermodynamics, each with its own approach and focus.
Okay.
Like, for instance, you've got classical thermodynamics,
Okay.
which deals with macroscopic systems near equilibrium, the kind we can observe and measure directly.
Okay, so that's like the practical side of things. What's happening in the engine of my car?
Exactly. But then we have statistical mechanics,
Okay.
which dives into the microscopic world. The realm of atoms and molecules. It seeks to explain those macroscopic properties that we observe by looking at the statistical behavior of a huge number of particles.
So it's like zooming in from the big picture to the tiny details.
Well, precisely. It helps us understand why gases exert pressure, how materials change their properties at different temperatures, and even how information is stored and processed at the molecular level. It's fascinating stuff.
That is fascinating. Okay, so we've got the big picture. We've got the tiny details.
Right.
What about chemical reactions? Does thermodynamics have anything to say about those?
Absolutely. Chemical thermodynamics, that's all about how energy is involved in chemical reactions and physical changes of state, like melting, boiling, freezing. It helps us predict whether a reaction will occur spontaneously, how much heat it will release or absorb.
Wow.
And what factors can influence its equilibrium.
So chemical thermodynamics is kind of like the recipe book for chemists. It's telling them how to cook up new materials and control chemical processes.
That's a great analogy. It's all about understanding the energy landscape of chemical reactions.
Okay. This is all incredible. But I'm starting to realize, we've been talking a lot about systems and equilibrium.
Yeah.
But most things in the real world, they're constantly changing, right?
Right.
Like the weather or a living organism. So how does thermodynamics deal with those dynamic, out of equilibrium systems?
That's where things get really interesting and honestly a bit more challenging.
Yeah.
Equilibrium, it's kind of a simplified state that we often use as a starting point.
Okay.
But most of the universe is far from equilibrium.
Right.
And studying those non-equilibrium systems, it requires a whole new set of tools and concepts.
It sounds like we're about to open up a whole new toolbox. I'm ready to see what's inside.
Yeah. So let's crack open that toolbox and see what we've got in there.
All right.
One of the most fundamental concepts in thermodynamics is this idea of a system.
Okay.
It sounds simple enough.
Right.
But it's actually really crucial for analyzing how energy flows and how it changes.
Okay.
So a system, it's just the part of the universe that we're focusing on.
Right, like a beaker full of chemicals or a car engine or something like that.
Yeah, exactly.
Okay.
We define the boundaries of the system, and that allows us to, keep track of the energy going in and out.
Okay.
Now, there are different types of systems.
Okay.
Depending on how they interact with their surroundings.
Okay.
So you've got isolated systems, which are completely sealed off.
Right.
No energy or matter can cross their boundaries.
So like a perfectly insulated thermos or something.
In theory, yes.
Okay.
Though achieving perfect isolation is practically impossible.
Right, of course, yeah.
But then you have closed systems
Okay.
where energy can be exchanged with the surroundings.
Okay.
But the matter stays put. Like, think of a piston in a cylinder.
Okay, so heat can flow in or out.
Yeah.
And the piston can do work.
Right.
But no gas is actually escaping.
Precisely.
Okay.
And finally, you have open systems.
Okay.
Which are the most common in the real world.
Right.
Both energy and matter can flow freely across the boundaries.
Right, like a pot of water boiling on a stove.
Exactly.
Heat is going in, steam is escaping.
Yeah.
Very dynamic. Okay, but once we've defined our system, how do we actually describe what's happening inside of it?
Well, that's where we use these concepts of states and processes. So a state, it's like a snapshot of the system at a particular moment in time.
Okay.
It's defined by properties like temperature, pressure, volume, internal energy, entropy, all those things we've been talking about.
So it's kind of like a set of vital signs for the system.
Yeah.
It's telling us exactly what condition it's in.
Perfect analogy.
At that moment.
Yeah.
Okay.
Now, process. It describes how the system changes from one state to another.
Yeah.
It's the pathway it takes.
Okay.
And these processes are often characterized by things like heat transfer or work being done.
So if I heat that pot of water on the stove,
right,
that's a process that changes its state.
Exactly.
Increases its temperature, maybe turns it into steam.
Exactly.
Okay.
Now remember those conjugate variables we talked about earlier?
Right, the linked pairs, pressure goes up, volume goes down, that kind of thing.
Exactly.
But how do those conjugate variables relate to the energy of the system?
Well, they tell us how energy is being exchanged with the surroundings.
Okay.
Either as work or as heat.
Right.
For instance, when you compress a gas, you're doing work on the system. And that can change its internal energy.
Okay.
Or when heat flows from a hot object to a cold one, That's also a form of energy transfer.
Right.
And it's related to the change in entropy.
Okay, that makes sense.
But I'm still a little fuzzy on how we actually measure the energy content of a system.
Yeah.
I mean, can't we just, like, stick a thermometer in there and be done with it?
If only it were that easy.
Right.
While we can measure things like temperature and pressure directly, other quantities like internal energy and entropy, those are a bit trickier.
Okay.
That's where thermodynamic potentials come in.
Okay.
These are mathematical functions that allow us to quantify the energy that's available to do work under different conditions.
So they're like different lenses through which we can view the energy of the system.
Exactly.
Okay.
One of the most important ones is Gibbs free energy.
Okay.
Now, this tells us whether a process will happen spontaneously
Okay.
at a constant temperature and pressure.
All right.
So if the Gibbs free energy decreases,
Yeah.
the process is spontaneous, like a ball rolling downhill. If it increases, you need to put in energy to make it happen,
Right.
like pushing a ball uphill. So Gibbs free energy is like a predictor of whether a reaction will happen on its own or not.
Exactly.
That's incredibly useful.
It is. It's a cornerstone of chemistry.
Yeah.
And many other fields.
Wow.
It helps us understand everything from chemical reactions to the formation of crystals to the behavior of biological systems.
So thermodynamics is really about way more than just heat and engines.
Absolutely.
It's a powerful tool for understanding how the universe works at like a really fundamental level.
It's a universal language that applies to everything.
Wow.
From the smallest atom to the largest galaxy.
Yeah, it's really amazing to think that all these principles of thermodynamics, they govern everything. So the tiniest, chemical reactions to the evolution of the whole universe.
It truly is a unifying theory.
Yeah.
And you know what? It's still a very active area of research.
Oh, really?
Oh, yeah. Scientists are constantly pushing the boundaries of thermodynamics, exploring those non-equilibrium systems, developing new tools.
Wow.
And finding new applications in fields like nanotechnology, information theory, even economics.
It's so cool how it just kind of pops up everywhere.
It really does.
It does. It does. But for those of us who aren't scientists,
right.
What's the takeaway here? Like, why should we care about thermodynamics?
Well, because it helps us understand the world around us at a deeper level. It explains why things happen the way they do.
Okay.
From why your coffee gets cold to why batteries run out of power.
Right.
It gives us insights into the efficiency of engines, the limits of computing.
Wow.
Even the direction of time itself.
Yeah, it's not just some abstract theory confined to textbooks and laboratories. Okay, woven into our everyday lives.
Absolutely.
Yeah.
It's a powerful framework for understanding the flow of energy and the nature of change.
Right.
And the more we understand these fundamental principles,
the better equipped we are to make informed decisions about our technology, our environment, even our own lives.
Like thermodynamics gives us, I don't know, like a new lens through which to view the world. And it reveals all these hidden connections and underlying principles.
Exactly. And it reminds us that even in the midst of all this complexity and change, there are fundamental laws that govern how the universe behaves.
Right, right.
There's a certain elegance and beauty to that.
Absolutely. It's like glimpsing the underlying code of reality. Well, I think we've given our listeners plenty to ponder today.
I think so.
Any final thoughts before we sign off?
Just keep asking questions. Stay curious. Never stop exploring.
Yeah.
The world of thermodynamics, it's full of surprises.
Right.
Who knows what amazing discoveries are still waiting to be made.
It's pretty exciting.
It is.
It is. Well, hey, thanks for joining us on this journey into the world of thermodynamics.
My pleasure. It's been a real eye-opener, for me at least. Glad to hear it. Yeah. All right, everybody. Thanks for listening. We'll see you next time.